Welcome everyone to geometry. Today we want to take a look at section 20, which is all about circles. We're going to start off with just a definition and a theorem that I believe everyone is familiar with, and create several hopefully shorter videos for this section. So, a circle. What is a circle? Well, it's exactly what we are familiar with it being, right? It consists of a center and a radius, which gives a collection of points that are a fixed distance away from that point, called the center. So given a point and a positive real number, the circle centered at that point with radius r is, right, it's just the collection of points which we denote by C. So that's just a C, and then parentheses O, R. So circle centered at O with radius R is the collection of points P. Maybe we want to give it a capital P there. All the points P such that OP, right, the distance from O to P, is equal to R. Of course, that makes sense here, right? Distance from from the center to a point on the circle is the radius. We're familiar with that. So again, O is called the center, and we use the word radius in two different ways. We use the word radius to describe the distance from the center to points on the circle, but we also use the word radius to describe the line that's drawn here, the line from the center to any point on the circle. So a quick note here that a lot of times it won't be a specific number that's given, but what will be given is 2 points, right? The center and a point on the circle. So a lot of times we will denote the circle by a circle, right? C with center O and radius OA. That's a distance there. All right. So circle, exactly what we expected, exactly what we're familiar with. Maybe an introduction of notation. So let's take a look at our first theorem. 3 points determine a circle. Now that I think that we're familiar with as well. We may even be familiar with how to find a circle given 3 points. And that's exactly what we want to use. So if you're familiar with that already, then you know what's coming. But if you're not familiar, then what we're going to use is perpendicular bisectors. Use the perpendicular bisectors to find a center. And that's essentially what we're going to do, all right? So let's take a look at how that plays out. Well, let's start with 3 points. So let's take points. Let's make that a little bit bigger. A, B, and C. That looks pretty good. All right, so if we have points A, B, and C, then what we want to do is we want to find the lines between AB and BC. So the line from A to B and the line from B to C. And then what we want to do is we want to create the perpendicular bisectors. So let's see. That's not quite the perpendicular bisector. Let's move it over a little bit. That looks close enough. And perpendicular bisector. I think that's a little bit off yet too. Well, that should be close enough anyway. Gives us the idea. So perpendicular bisector, perpendicular bisector. Again, we will write all this down. So we have a pair of perpendicular bisectors, and they cross at this new point we'll call P. Okay. So this is the center of the circle. And we know that it's the center of the circle because this point is the same distance from A, B, and C. Well, how do we know that? Well, a point P lies on the perpendicular bisector of AB if and only if it is equidistant from A and B. But the same is true for a perpendicular bisector of line segment BC. It's the same distance, right? P must be the same distance from B and C. So we use the transitivity of equality to get that P is the same distance from A, B, and C. Once we have that they all lie on the same circle with center P. Excellent. So that's the idea. That's what we're going to do. So let's let A, B, and C be three non-collinear points. It's very important that they're non-collinear. If they were collinear, think about what would happen there. And I'll let you fill in the blanks for that. But let's let A, B, and C be three non-collinear points. And let's let M be the midpoint of the line segment from A to B. So this right here is M. And let's let N be the midpoint of the line segment from B to C. So this point here is N. Right, we needed to identify the midpoints because we can then implement the perpendicular existence theorem, perpendicular line existence theorem. Forget what it's called. Anyway, we want to implement that. Right, there exists a perpendicular to a line through a point. And in this case, we're specifically looking for the perpendicular bisector. So we get that by considering the midpoints. All right, so then there exists line L such that L is perpendicular to AB, and actually here let's perpendicular to AB, and it's through the point M. So it's through the point M, and there is line M such that M is perpendicular to line segment BC, and it's through the point N. So perpendicular through N. So we've already drawn the picture, right? Now we're writing down what's going on here. So we have these lines, lines L and M. L and M intersect at point P. Now, one very important question here is why? Why do they intersect? And I would expect that you would be able to answer that question. So why do they intersect? Please make sure you can tell me. So since P lies on the perpendicular bisectors let's see here. We have that the distance from A to P is equal to the distance from B to P. So AP equals BP. And because it's on this perpendicular bisector, BP is equal to CP. Now that is AP is equal to BP, which is equal to CP. That gives us, hence, A, B, C all lie on the circle with center P and radius AP. Of course, you could have chosen radius BP or CP. It's all the same thing. But that's what we wanted. So there might be, you might ask yourself, well, aren't we missing one more thing? Yeah, we're actually missing uniqueness. How does this show that it is unique? Or how can you show that it is unique? So that would be good to be able to identify as well. But that's all that we wanted to talk about for this first video. So I'll see you guys again soon, continuing on in section 20.